Okay, so here we are again, moving on to chapter 2. This is termed geometric optics and image formation, also just called optics sometimes. And last chapter we looked at reflection and refraction. Now we're going to see how reflection and refraction can form images, optical elements, and those properties to form images. Alright, so this is a pretty neat little picture of an image being formed by this weirdly shaped, mostly sort of convex mirror, spherical mirror. We'll talk more about those a little later. Just wanted to say that give you an idea of the general approach that we're going to be taking, which is basically to introduce an optical element, general name for stuff like mirrors, lenses, that sort of thing. Then we'll use ray tracing, using the idea of light moving as rays in straight lines. We use ray tracing along with our understanding of reflections and refractions, how those work, in order to see where images are formed. And we'll kind of go a little bit more in detail in places and derive some of these relations, all the particular variables, things going on there. And then sometimes maybe look at some of the issues that come up or arise with those particular optical elements. So that's the general approach. The first optical element we're going to look at is the plane mirror, essentially the simplest kind of optical element, just a flat reflecting surface. Here we see that flat mirror as well as an eye to represent where we're going to be looking at this mirror from, and an object placed in front of the mirror. We have a number of things detailed on there, some points like point P, P prime, the bottom, the top of the object. We have B, A, where there's other points, Q, Q prime, and also these D0, or D sub, technically sub O, D sub O and D sub I, which are going to come up a lot in this chapter. So the object, the thing that's light is leaving from, and it's going to interact with these optical elements and then form images, that's what we just call the object usually. And then where that image forms, well, call it the image. So DO is the distance from the optical, well, it's going to be the way we define distance from the element can change a little bit because some of our elements are curved, but generally it's just the distance from the optical element to the object, and then DI is distance from the optical element to our image. If we look at this picture, we can see some rays. Right, we propagate some rays, say from the bottom of our object, from point P. And remember, we can sort of think about two rays leaving from the same point. There's many, many rays of light leaving from that point, but two rays that are at a very small angle from each other leave that point, and then they're going to strike the mirror right around point A there. And our law of reflection just tells us that the reflected angle, remember the angle is measured from normal from a perpendicular line, the reflected angle is going to be the same as the incident angle. So you just get this same reflected angle coming back out. That one of the rays is going to go up, the other one's going to go up at it's going to hit a little bit higher and go up slightly higher, right? And as I mentioned in the last chapter, our eye will trace those rays back and sort of project them back past the mirror until they actually meet at this point Q. So the bottom of the object became the bottom of the image over here. Same idea with P, or P prime, right? Go through that whole process. Looks like we actually get to talk about it here. Turns out with mirrors, and you know this from just looking at mirrors, the objects in mirrors appear as essentially the same size as they are. They appear behind the mirror, where the light rays aren't actually going. There's never any light rays actually there, it's just our eyes projecting in there. Well, besides that, the way that we measure distances to objects and images, these are called some sign conventions, and conventions can be slightly different depending on who is deciding what the sign convention is. For us, for the flat mirror, we're essentially saying that the distance from the mirror surface to the object is positive, and the distance behind the mirror, where the image always forms for flat mirrors, is negative. And a couple of things I kind of mentioned already, but we'll get into more detail in the next slide. I just wanted to point out that this image, since the light rays aren't actually crossing to form this image, our eyes are just projecting them, this is what we call a virtual image. It's also upright. It's the same orientation top to bottom as the object, and it's the same size as the object. It's not larger or smaller. So I pointed those things out because in general, when we're looking at images being formed, there's these sort of three categories, classifications that we use to talk about that kind of image that it is. So in the case before, it was a virtual object because there's no actual light rays that pass behind the mirror and converge on that spot. So that was a virtual object. Real images are formed by where real light rays pass through, and one way of thinking about that is that a real image, if you have a real image, then you can essentially imagine putting a screen at that location, and the image, you'd be able to see the image on there, it would be projected on there. So in the case of the mirror, if you took a screen, put it behind the mirror, you won't actually have any image to project there because it's a virtual image. The other classification is, well, is it upright or is it inverted? Meaning, is it the same top to bottom, or does it get flipped over to the bottom now, the top of the image? Lastly, is it larger, smaller, or the same? This has to do with the magnification, which we'll definitely talk about multiple times as we go through for different elements. These are just some interesting examples of arrangements of plane mirrors. I'm not going to worry too much about them, but you've probably been in some of these situations. If you have two parallel plane mirrors, you essentially, due to the reflections happening in the virtual images being formed, you can essentially end up having infinite images formed. And actually in this figure and in the description of the figure, it sort of points to the answer to the question that I posed in the last lecture, or the last chapter, in that flat mirror are actually inverting front to back, not left to right. And then there's also this other setup where you have these two perpendicular parallel mirrors, and you can form an image that's in the corner, essentially behind the corner. You can see that image in the purple-ish sort of arrows that are leaving the object, and they end up getting reflected twice in the corner and come back, and that image gets projected right back there, back behind the corner. Okay, so plane mirrors, not that interesting in the end. They only form one kind of image via reflection. And we're going to move on then to what's known as a spherical mirror. Also will form images via reflection, but now our reflective surfaces are curved. And they're called spherical mirrors because essentially they could be made always, you could think about them always as being cut off sections of a sphere. So if you were to cut off, say, the left side of that sphere, imagine a 3D object, but you cut off the left side of it and sort of silver the inside of that sphere, and we get this top spherical mirror, which we would call a concave mirror. A concave thing that's caved in, or the reflective surface is caved inside. And if you took the other side of that sphere and silvered the outside of it to make it reflective, then we would create the convex mirror, right? The reflective part is pushed out. You can see these are very simple diagrams of light rays approaching those two different kinds of spherical mirrors. A couple of things to note here. Well, for one, when we're talking about these spherical mirrors, oftentimes we're pretty much always going to have diagrams, and then one of the principal things to look at or to draw on is the optical axis, which is essentially like an axis of symmetry for these elements. Axis just goes right through the center. And then the point where it goes to the center is the vertex of that mirror. There's also the center of curvature of a mirror, spherical mirror, which is the radius of curvature of whatever that sphere that it was cut from was. So looking at basically just the concave mirror, spherical mirror for a second here, it turns out that in forming images, it's really nice to focus light rays to a particular point. And the best kind of curved mirror to do that is actually the parabolic mirror, because the surface turns out to be that or the curvature makes it such that all the light rays that come in parallel anywhere on the parabolic mirror are going to focus to one point. Whereas with spherical mirrors, depending on how sort of curved it is, you actually can have your light rays that come in parallel will focus at different points. It's not really ideally good aberrations that way. So when you're talking about spherical mirrors, you're generally thinking, spherical mirrors, you're generally thinking of two kinds, where it's either large or small, and that is relative to the radius of curvature of that mirror. Or another way of looking at that is like, if I imagine the large spherical mirror here, if I imagine extending it out to be a full circle, it's a little bit tighter right here. The circle that it's actually going to form is not that much bigger than the mirror there, right? The mirror is actually a fairly large chunk of that circle. Versus the small spherical mirror, if I imagine extending the form out here, right? It's a bit wider. The circle that it forms is fairly large, so that spherical mirror is a small section of the sphere that it was taken from, or hypothetically taken from. So everything is small versus large is like small section relative to the full circle. And as it turns out, when you have a small mirror like that, it acts pretty similar to the parabolic mirror, meaning that any light rays that come in parallel to the optical axis are going to focus to a single point. We call that the focus of the mirror. So we're going to actually focus mostly on these small spherical mirrors. So when we're talking about spherical mirrors, kind of the next few slides or the next little bit, mostly just thinking of small spherical mirrors. Parabolic mirrors are very nice, but they're actually very difficult to fabricate and produce. So oftentimes, in practice, you'll have small spherical mirrors instead of a parabolic mirror, which you might want. So not to leave convex spherical mirrors out, a little diagram of a convex spherical mirror. Again, we're just thinking of small mirrors. Right? This is a small section, a larger circle if you were to extend it out. And we care about that again because that approximates the parabolic mirror, and so those actually, the light rays come in parallel are going to focus in a certain sense, so they're going to all act in the same way. For the convex mirror, the light rays that come in parallel are actually shot, they're reflected back out in this sort of sprayed out manner in such a way that if you were to project them all onto the other side of that convex mirror, they would all cross at at that one point, the focus of that mirror. So essentially when those parallel light rays come in, they get reflected as if they come from the focus of the convex mirror. Now we have a new optical element, technically, or alternating versions, two different versions of this optical element, the concave and the convex reflecting spherical mirrors. So let's go ahead and try out some ray tracing, or give you sort of the way to do ray tracing with these mirrors. And these diagrams, a little complicated, maybe not the best, but let's say, just take the first mirror, this concave mirror, and we'll just go through each of these numbered rays. So this is the way that we would figure out visually where the image of an object will form. So take the object, which you generally just draw as an arrow, where the base is on the optical axis, and then that arrow tip is the top of the object. So P to Q. And the first ray we can draw is a ray that leaves the tip. All these rays are leaving the tip of the object. The ray that leaves that tip goes parallel to the axis, the optical axis, and since it's going parallel, it's going to be reflected back to the focus. Right? It's the whole point of this convex spherical mirror, this small convex spherical mirror. Right? So that's one ray. The second ray we can draw is one that essentially is a reverse idea. That is a ray that's going to go through the focus, and essentially since it went through the focus, it's going to have to be reflected parallel to the optical axis. It goes through the focus, goes parallel. And so that ray 1 and ray 2, turns out with just two rays, you can pinpoint where the image is going to be, right? P prime, Q prime, that's our image. A third ray, or even a fourth ray, is more of just like a check. But the third ray you could draw is one that goes through the center of curvature of that mirror. since it goes through the center of curvature, essentially it's like it's going along the radius of that sphere, meaning when it hits the edge, it hits directly perpendicular to that surface, and so there's no reflective angle, it just goes straight back. So that's why we get ray 3 that just goes straight through the center of curvature, hits the mirror, and comes back. Still showing us that the tip of our image is right there. And then there's a fourth ray you could draw. It's not typically drawn a whole lot, which is the ray that leaves the tip of the object, hits at the vertex, and is reflected at the same angle back down. So it's here, whatever angle it came in with the optical axis, the law of reflection tells us that it reflects at that same angle below. That was not typically drawn a lot because you kind of have to have a protractor to really draw it very well. And then one other thing to note is that there's kind of assumed that if we're finding the height of an object, we kind of need where the top and the bottom is, but any ray that's going to leave the bottom of the object, we can think of a ray that just goes straight along the optical axis, and that ray would get reflected straight back, because again, it hits it perpendicular to the spherical mirror. And then so these same rays could be drawn, that we just talked about this, or I just talked about this on the concave mirror. They could also be drawn on the convex mirror. Then the first ray we would draw is, again, the ray that comes in parallel, and it's reflected through the focus, but the focus is on the other side of the convex mirror. The focus is on the inner side here. And so talking about reflecting along that line that would go from that point to the focus. Right? So it actually comes in and gets reflected along that line and back up. The second line is one that goes directly towards the focus, and then it's as if it came from the focus, and it's going to be then reflected parallel still. And again, those two rays can pinpoint it. You can test a third ray, which would be one that goes straight towards, it would be straight across to the center of curvature, and it would come straight back, and then also the fourth ray there. So in that ray tracing, the focal length, or the focal point where the parallel rays converge, is a very special point. So we want to try to relate that to physical aspects of the mirror, like the radius of curvature of the mirror. We already have it shown here, so we're not going to walk through the derivation. We just talk it through a little bit, and hopefully you'll see how we get to that. So the first thing to note is, again, we're talking about small spherical mirrors, for one. Right? So this mirror is fairly small compared to the radius of curvature if you were to draw out a full circle mirror. And then on top of that, we're going to need what's called a small angle approximation. And we're actually going to use a small angle approximation pretty regularly throughout this chapter. So what that means is that when the angles we're talking about small, what small means in terms of the angle is about 10 degrees-ish. At least, maybe probably less, maybe is around that area. We'll say a little bit more about that later too. So, we were talking about small mirrors, and we allow this small angle approximation. Then we can just kind of step through this proof here, where we start out looking at r. Right? R is the distance c to x, also the distance c to p. This is the radius of the mirror here, or the radius of the circle. And c to p we can break down into cf, and then fp. And if you look at the triangle cfx that's formed there, and you can do some geometry to convince yourself that those angles, well, it's essentially they're parallel rays and you have alternating interior angles, those are the same angles. So that triangle CFX is an isosceles triangle, meaning that CF is the same as FX. Right? So then we can go to FX plus FP. And now is where we use a small angle approximation to say that FX is essentially equal to FP. Doesn't necessarily look like it here in the diagram, because again, well, not again, I don't know if I said that already, but this diagram is greatly exaggerated. Those angles are much greater than 10 degrees. When it's more for clarity, you know, if you blow everything up, it's a little easier to see. But in truth, the angle that we're talking about, FXP, the triangle might look a little bit more like this one down here, where it's essentially a triangle with a very narrow side on one side, meaning that the sides FP and FX are essentially the same length in that small angle approximation. we're talking about here. So fx plus fp can become fp, or 2fp, which, when we look at the diagram, fp is the focal length, so that's twice the focal length, right? All that focal length is 1/2 the radius of curvature for our spherical mirrors. Right, so now we have the relation of the focal length and the radius of curvature. We also are going to want to know how the focal length depends on, or how it's related to, the distance that we place the object and then the distance that the image is formed. So that's kind of the goal right now, is to relate those. The book actually derives this relationship one way. I'm going to do it just a slightly different way. But again, both of those ways rely on the small angle approximation. And in that approximation, we're talking about fairly small angles. Sine of theta is essentially equal to theta. Cosine of theta is essentially equal to 1, which means tangent of theta is also essentially equal to theta. So, using that. All right, well, let's go ahead and see if we can relate the focal length and the distance to the object and the distance to the image. So like I said, this is a slightly different derivation from the book, and it mostly relies on looking at considering two of the triangles that are formed by these rays. Right? So we're using the rays from the object. One is the ray that we have number 1 in that list of ray tracing, which is through the focus. One or two, I actually don't remember right now. But there's a ray that will go through the focus and then come back parallel. And then we actually are going to use that last ray, which is the ray that goes straight to the vertex and then is reflected back at the same angle. So those two rays will meet back here at our image. We'll form a real image, real inverted image there. And yeah, so what we're going to be considering are, these two triangles, O prime A, or O prime, and O prime, right? And if we look at those in the diagram, they're actually similar triangles, right? They're both right triangles and they share an angle. So these two angles are actually the same. And what that means is that we can write ratios to relate the different sides. Namely that for the O1, the height of that is the height of the object. For I1, the height of that is the height of the image. So, height of the object or the height of the image, we can relate to, write as ratio to the two other sides here, AO and AI, which actually happen to be the distance to the object and the distance to the image. Okay, so that gives us a relationship between our, gives us a use. Understood. The next thing we want to consider then to get to a relationship we're interested in is some of the other triangles, which we could look at as the triangle O prime F, or O prime, however you want to say it, and then also the triangle FAB. There's going to be an approximation here where that's section A to B is actually a curved section, but we're talking about small mirrors, so this curvature is very small, and we can essentially approximate that AB as being a straight section here. If we do that, then again we're dealing with similar triangles where these two angles are the same. That angle O prime is just opposite the other angle, right? So they have to be the same angle. So again, we can write another kind of relation, which is the ratio of these heights is going to be equal to the ratio of OF to FA. And then if you look at OF, we can actually write that as the distance to the object minus FA. And then finally, FA is the line segment, but that's actually the focal length. F is that same distance. And given our first relationship that we have up here, we can now get rid of the heights altogether, and we get this relationship. And then just a bit of algebra. Go through it, not go through it. Well, I'll write it down quickly. C well, however you want to do this. And then we invert both sides. This becomes 1 over f. And when you invert, then break up this fraction, the extra term, do or di is going to cancel it here, and we're going to be left with yeah. So this is what we would call the mirror equation. Right. Yeah, there it is, mirror equation. And again, valid for small angles, and we're talking about small mirrors still. And it's also valid for, we derived it for concave, or I just showed you the derivation for the concave mirror, but it's actually true also for the convex mirror. You might look at that in maybe in a class meeting or something. Okay, so the next and sort of last complication when talking about an optical element is sign conventions. You can decide what you want to call positive and what you want to call negative, and that will result in your convention, and you just got to stick with it, right? So it's not necessarily, well, it's a little bit arbitrary what you decide to begin with, but then everything kind of has to follow from there. So in each of our setups, we're going to need to remember that there are sign conventions for when we're actually trying to like plug in, say, the object distance or the image distance or the focal length, right? Those things can be positive or negative. For spherical mirrors, the first sign convention are about focal lengths. Focal lengths we're just going to say are positive for concave mirrors, this kind of mirror, and negative for convex mirrors. The image distance is positive for real images and negative for virtual images. So if light rays actually converge to a point to form the image, we call that a positive distance, wherever that distance is. And if the light rays don't actually converge, they're projected. It's a virtual image, then negative distance. Another way to put both of those two things together is essentially to say if something's on the reflective side of the mirror, it's positive. Otherwise, it's negative. And then the last thing, this is one that kind of carries through most of the things where the height of the image is positive if it's upright, right? The top of the arrow is still the top of the arrow. In the image here, that's actually inverted, so the height would be negative. Yeah, and so these sign conventions are important for multiple things, but these are the sign conventions that are essentially implicit in the derivations that we might do or the equations that we're going to use, how they're written in this text. So if you're going to use the equations, you should need to follow these sign conventions. And finally, you might have noticed, the height of the image might be different than the height of the object itself. In this case, the height is a little bit smaller. So we define something called magnification, technically linear magnification here, which is just the ratio of the image heights to the object height. That is related then to the distance of the image and distance of the object. It's maybe a little bit confusing, but by convention, the magnification is equal to the opposite of the distance from the image divided by the distance of the object. Yeah, all the other stuff about magnification is pretty straightforward. If the magnification factor is greater than 1 or below -1, then the image is going to be larger. If it's negative, it's just inverted, but it's still larger. And then if the magnitude of the magnification is less than 1, then the image is going to be smaller. Time for an example. And this is kind of a neat one, just because it ties in to concept from the last course, or part 2 of this 3-part series. which has to do with heat transfer. In this problem, we're talking about solar power generation, and it has to do with the solar power generation. One way of generating solar power, or generating power from solar energy, from light rays from the sun, is to use spherical mirrors, and essentially, like those light rays that are coming in parallel, are all going to focus, get directed up to this one point to the focus. And basically, when you're talking about the sun, or any distance, any object that's very far away from our mirror, then all the light rays that are getting from that object to the mirror are essentially parallel. Right? If they weren't parallel, then they would have diverted off, and they don't actually hit the mirror. You know? This mirror is a very small thing to hit from the distance of the sun. So if we know, we're given some particulars about this setup, like the focal length of this mirror. Technically, these mirrors are parabolic, but usually they're parabolic, but we're going to treat them as spherical and use, so we can use our equations here. We assume it's like a small spherical mirror and it has this focal length. What's the radius of the mirror, for one? And then what is the amount of sunlight concentrated onto the pipe, assuming that this amount of power per square meter in insolation. I haven't really heard that term before, but it's not insolation with the U, insolation, meaning essentially like power radiated from the sun or the lands here on the Earth here. But if that insolation, 900 watts per square meter, how much is then concentrated onto our pipe, onto the focal, kind of focal line here now, because we got this long parabolic, this long spherical here. And then finally, if the pipe is this diameter and actually has mineral oil in it, how much energy is actually transferred to that mineral oil in a minute, and then how much does that raise the temperature of the mineral oil? And that's important because that heat from the mineral oil is then able to transfer over to something else, and essentially, just like any other way of generating electricity, you essentially use that heat to boil water to make steam, and then have a basic steam engine set up, and you can generate electricity that way. So let's give it a shot. Okay, so what's the radius of the mirror? Pretty easy to remember. The radius is twice the focal length, or the focal length is half of the radius. You know? So the radius is just going to be 80 centimeters. Okay, so then in the second part, we essentially just need to look at this as like a power per, let's say, per meter length of this this parabolic trough. So what is the area of 1 meter of this parabolic trough? Well, it's going to be, oh yeah, so I forgot to mention, the trough is 1/4 of this circular cylinder. So we're essentially looking at the area of a cylinder, and but 1/4 of that. 1/4 of 2 pi times the radius of the mirror, which we just found, 8 meters, and then multiply by the length of that cylinder. We're just going to do it per meter here. Put all those numbers together, it turns out 1.26 square meters. That's the area of 1 meter of this trough. And so if the insolation is impinging 900 watts per square meter, we just multiply that by the square meters to get 1130 watts, about a kilowatt almost. Okay, cool. So then if we want to see how much is that going to actually heat up the oil that's inside of that pipe, we've got to go all the way back to, we're talking about radiated heat transfer, so these are one of our go back to one of our good old heat equations. So what's the mass that we're talking about? Well, it's going to be, whatever the density of that mineral oil times the volume of that 2 centimeter pipe. So what does that look like? Well, write it out in a little bit more detail, where our radius is 1 centimeter, right? Half that diameter, 0.01 meters. Yeah. And again, the density of mineral oil is something you gotta look up. Turns out it's 800 kilograms per cubic meter. Got pi, 0.01 meters squared, and the length we're talking about here is the 1 meter. Put all that together, it's 0.251 kilograms of mineral oil in that in 1 meter, this pipe. Okay, well, the next question real quick then is how much heat is actually landing on it, right? Because we've got power, but power is heat or energy per unit time, so essentially we just need to multiply that power by the time that we're talking about to tell us how much energy, how much heat is actually going to be transferred here. Because that looks like 1130, I'll write it as joules per second, so it's a little more clear, and we're talking about how much is transferred in a minute, or 60 seconds. Those seconds cancel out, and this is good because it should be units of energy. 6.78 times 10 to the third joules. And then finally we can, well, if we were to just divide our heat equation by the mass in that specific heat, then the change in temperature that mineral oil is going to go through is the heat divided by m and c. And well, I guess I still wrote it out here. This is just still as the power and the time. Put in that mass we found. And the specific heat of mineral oil is 1670 joules, kilograms per unit per Celsius, unit degree Celsius, or Kelvin. Doesn't actually matter here since we're talking about a change in temperature. All that turns out that we're going to change temperature of the mineral oil in 1 minute, 162 degrees Celsius. Quite a lot. Or maybe not extremely high, but it's a pretty good amount. Interesting example. The last thing to talk about for the spherical mirrors, very quickly, is what we call aberrations, which is essentially problems that come up when you're trying to make, the point is sort of just to make a nice sharp image, usually with these optical elements, and aberrations are things that cause that image to be fuzzy or just not well formed in a certain way. So for one, for the one that's shown here are spherical aberrations and cone aberrations. Spherical aberrations are essentially when we get far away from being, essentially far away from talking about small mirrors anymore. Right? All that stuff we talked about before had to do with small mirrors, being relative to the radius of curvature. When the mirror is not small anymore, then essentially these rays that are coming in parallel don't all get focused to the same point, which actually showed earlier on when we first introduced those. But essentially they get focused kind of to a line here instead. And then cone aberrations are when we're talking about rays coming in parallel, but not at an angle to the optical axis, not along the optical axis. So you can get other kinds of aberrations there, which sort of form these like concentric, not concentric, but like expanding circular sort of fuzziness going on. So that was all talking about reflection. You're using reflection to form images. And pretty much the rest of the chapter is on using refraction to form images until the very, very end. Get back and talk about reflection a little bit. One thing to note about images formed through refraction is something that we've seen all the time, or you see all the time when you're looking at objects that are like partially submerged in water. They have this kind of weird deformation usually to them. And one thing to understand, or one way to understand that property or what happens, is to trace out some of the light rays And when we do that in this image, or this diagram, you see the light rays that are coming from P. We extend some of those out, and what happens is they both refract the surface. The left one is at a shallower angle to the that normal line, so it reflects a little bit less, whereas this right line, light ray here from P, refracts a little bit more, so we get this sort of spreading out, and that way our eye traces those back, and they actually come together at this point Q. That's why you see, if it's just a rod, then it's, or objects in general, are going to appear as if they're a bit closer to the surface if you're looking down or down towards them. Right? And we can actually use our law of refraction and our nicely drawn out diagram to derive the relationship between where that object was, that point P, relative to where the image will appear, point Q, right? So this is what's called the apparent depth when you're looking down at objects in sort of usually in air to water. But so that's the relationship we'll get to here. We'll just look at a brief derivation. Mostly what we're going to need to look at are, again, more triangles, a lot of trigonometry going on in objects. And particularly the triangles we're going to consider are these triangles P, O, and R. So P from the originating point, O and R, that triangle. And then the triangle QOR. So for the image point, Q, O, and R. So the same ROR, that's the shared side of these triangles. And if you look at the drawing, then those two vertical dotted lines are parallel, and the ray from Q going all the way up, just cutting through those, which means that angle theta indicated there is the same angle for OQR, right, for that bottom of the triangle there. So what we're going to do, label that, I'm actually going to call that theta 2, because that's the refracted angle, and then the angle that P makes with the vertical, or the light ray from P makes to the vertical, is the incident angle. So let's go reach back and pull out our law of refraction, or Snell's law. And we're going to rearrange this. Oops, oh, I missed that too. And mess that up. So I have all the index of refractions on one side, the sign on the other, and now we're going to say that these are small angles, relatively small angles that we're looking down into, which means that sine of theta is essentially equal to theta. I guess I could write here, this is what's labeled theta in the original diagram. Okay, so then looking at the triangles, we can use some trigonometry to relate these angles and side lengths, where that triangle, well, essentially going to take the tangent of both of these angles, and the tangent is the opposite over the adjacent side, so OR over the adjacent side, which for one triangle is the height of the object, for the other triangle is the height of the image. Pretty straightforward. So tangent of theta 1 is that OR, that side length, over height of the object and tangent of theta 2 is also OR, but over the height of the image. And again, in that small angle approximation, the tangent is essentially equal to the argument of the tangent, right? Tangent of theta is essentially equal to theta. And now if we just go ahead and divide those two relationships, we can get this, and going back to our law of reflection, it allows us to relate to those indexes of refraction. And then you just multiply by height of the object to get to where we imagined we were going to go. That's apparent depth for you. Should note though, we use the small angle approximation, and you might be thinking, well, it's not always a very small angle we're looking at, so that derivation doesn't necessarily work in that condition, but once you get further away from the small angle approximation, then you can still derive a relationship. It's just more complicated, and you sort of have these corrections to that small angle, which we might look at, or maybe we'll look at in the class meeting at some point.